started here. Good morning. Okay, so last day we finished, last day was Monday. I'm losing it. We finished chapter 2, so we wrapped up 2.8, and I can't remember, I feel like we said we were just gonna jump right into chapter 3 because we kind of ended on a high note. Oh yeah, let's see here. Yeah, we talked about the inverse, confirming that it's the inverse. Okay. So just as a quick review, let's see if I can go there in my mind. Feels like a lot's happened since Monday. It hasn't, but just busy week. So we talked about, let me flip back there. We talked about functions being one-to-one. So we finished chapter 2, and it's crazy. Chapter 1 and chapter 2 just take so long to get through. And then we'll just touch in chapter 3 today, and then we'll move on to chapter 4. So don't worry, we are kind of getting through it. So chapter 2, so we talked about one-to-one functions, right? If we can show, so a function is one-to-one, oopsies, haha, why does it keep doing that? I'm too fast. So if we can show, if we let f of a equal f of b and are able to show that a equals b, right? If we force f of a to be equal to f of b, and then we're able to kind of, everything falls out and a equals b, then the function is one-to-one. The function is one-to-one, right? Which just says that if you have the same output, well, those inputs would have to be the same. So there's no way to get the same output for different inputs. If you think about x squared, for example, I can put in x equals -2 and get 4, but I can also put in x equals +2 to get 4. So I get the same output for different inputs. That's not one-to-one. So if it's one-to-one, it just says that, well, each input yields unique outputs. And we show it mathematically by doing this. Right. We also talked about doing it graphically, but that was last week, so I'm gonna leave that. This one's more important. So then the function is one-to-one, which means it is invertible. Right, that's why we care. Okay. So then we talked about the inverse of a function, which we denote f to the power of -1 of x. Okay, really important that the -1 is on the f and not on the f of x, right? F of x to the -1 is just 1 over f of x, whereas here, this -1 is just on the f, which is how we denote the inverse. Okay, so here, let's make a note. How do we find the inverse? Right, we did quite a few examples last day. So what we do is to find the inverse of f of x, okay. Step 1, right, y equals f of x. So y equals the function, right, x -2 over x plus 2, for example. Then solve for x. Solve y equals f of x for x. Sorry. Here, everywhere. Okay, so you have y equals f of x, and you're going to solve for x. The other option is you can swap your x's and y's and then solve for y if you prefer to solve for y, but let's just keep it simple and follow these steps. So you're going to solve for x. Okay, so you're going to rearrange everything in terms of x, and then swap x's and y's, and the result, result is f inverse of x. Okay, so whatever you find there is your inverse function. Okay, and then, so we talked about, okay, well, a function has to be 1-to-1, and then we're able to find the inverse. Once we have the inverse, we can confirm that we have the inverse using the cancellation properties. So confirm that the inverse we found is in fact the inverse using the cancellation properties. Is that what we were calling them? Sorry, let me just confirm here. Yeah. Right. F of f inverse of x has to be equal to x, and so we have to prove it both ways, and f inverse of f of x is equal to x, right? So we have to show both. So if I stuff the inverse into the original function, all I should be left with once everything kind of trickles down should be x. And same thing, if I stuff the original function into the inverse, everything just kind of cancels out, and I should be left with x. If you're able to show this, then the inverse that you found is the inverse of the original function, and vice versa. Okay. So that's the end of our review.
Oh, quick question.
Sure.
Since on the 2.8 hand-in sheet, it was state the domain of the inverse function. I can't remember. Did we? Yeah, we probably touched on that, but.
Yeah, but that would be really good to talk about.
Yeah.
Thank you. Or just in the review. So the domain of f of x and the range of f of x. So if we let A be the domain, so just kind of naming it, the domain of f of x, and let B be the range of f of x. Okay. What happens is all the whole domain becomes the range, and the range becomes the domain. So I'll do it in a different color. Then f inverse of x has domain B and range, oops, I don't know why I tried to capitalize that, and range A. Okay. So I guess what I wanted to say was that they have the inverse for the domain and the range, which is true, right? And so the inverse has the domain, which used to be the range of the original function, and the range of this thing is the domain. So one thing you can do here is I actually find that it's easier if you, because it's easier to find the domain than the range sometimes, right? The range is the output values. Sometimes it can be hard to figure out, okay, well, what output values could I get here? And so it's easier if you find the domain of f of x, and then also find the domain of the inverse, right? So just look at the inverse. I'm not allowed to divide by 0, so you have to pull those out. I can't take the square root of a negative number, right? I can't take the log of anything but a positive. And so we haven't really touched on logs quite yet, but I think Shaun's kind of sprinkled them in somewhere. And so in some places, so it's easier to find the domain, right? So if you have the inverse, then you can find the domain, and then the domain that you found is the range of the original function. And then you have the range because it's the domain of the original function.
Okay, so what I ended up doing was just finding the domain of the inverse function. And so that was one of the correct ways to go about it, yes? Okay,
exactly. Awesome. Good. Cool beans. All right. So, like I said, we're just gonna kind of duck into chapter 3 briefly. We're gonna talk about quadratics. You've already touched on quadratic functions in chapter 1, I think it is. But we're gonna put some time into plotting quadratics, talking about how do we use quadratic functions, and then we'll get out of here. So chapter 3 is polynomial and rational functions. Hey Jared, do you need help?
I think I'm okay, thanks for.
Okay.
I'm good.
Okay. So 3.1 is the only section that we're going to do, which is on quadratic functions and models. Quadratic functions and models. Okay. So, just as a little refresher, right? A quadratic is anything of the form that looks like this. F of x is ax squared plus bx plus c. This here is a quadratic. So a quadratic function is a polynomial degree 2. Okay. Polynomials are just anything where you have a series of x's to varying powers, but you don't have anything, you hate to say nasty, but you don't have any kind of square root of x or anything like that. You just have straight x's, so x to the power of 1. Technically, it's c times x to the power of 0. Anything to the power of 0 is just 1, right? So that's really useful to keep in mind. Right, and so here you just have coefficients multiplying your x's to varying powers. And then for your degree, remember for a polynomial, poly means many, nomial means terms. So here we have multiple terms, right? Boom, 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 3 in this case. And degree 2 is referring to the highest power of x, right? So the highest power of x is 2, and so if you have a quadratic, it's going to look something like this. You can let b or c be 0, right? But a can't be 0 because what happens if a is 0? Well, the x squared term goes away and all of a sudden you have a linear function, right? Note that a cannot be 0 because then f of x would be linear. Would be linear, right? But b can be 0, right? And c could be 0 if we wanted to. As long as we have some sort of x squared term, then we have a quadratic function. Okay. So the easiest way to graph quadratic functions is to put it into standard form, so what we call standard form. Let's write that out. The easiest way, well, I guess the easiest way is to graph it in Desmos, which I'll show you how to do. But for us, we need to be able to just sketch graphs of quadratics. It's one of the things you're expected to take out of this course. And so the easiest way to sketch a graph of a quadratic is to put it into standard form. Standard form looks like this. F of x is a times x minus h squared plus k. Okay. To get here, okay, what we have to do, so what we're doing is we're going from this, now I can't remember what it's called, general form, I think it's called, but I don't want to commit to anything because I don't quite remember. I think this is the general form and this is the standard form. Doesn't matter. As long as you remember that this is the standard form, the one at the bottom. I want to have them on the same screen, so it's hard. There, how about? So this is the standard form. Okay, and I'll underline that here. Okay. So what we do is we put it in standard form, but to get from here, so this general form, to standard form, what we have to do is we have to complete the square. Probably sounds vaguely familiar. I did ask Shaun if you had covered completing the square, and he says you have. Whereas I kind of put it off until this section, so, but we'll do a little refresher, okay? So what we do is to go from f of x equals ax squared plus bx plus c to f of x equals a times x minus h squared plus k, okay, we need to complete the square. We need to complete the square. Which is from section 1.5. Section 1.5. Okay, what I'm going to do is I'm going to pull it in. Let's see if I can find it. .6, no. Fundamentals, part 2, I think. That's 1.4. I'm just grabbing. Here it is. Whee! Way up here. Okay, so we have to complete the square. I'm just going to have that there for reference. And you know I post these notes afterwards, so you don't have to kind of rush through and maybe just leave yourself a little bit of space. We'll just kind of come back and talk about it. It's a little bit harder than I want to do with just the general terms. You can work through it on your own time and just work through the general terms. But I want to do it with completing the square with an example instead. So let's just parking lot completing the square for a little bit and just remember that that's how we move from here to here. Okay, so just parking lot that in your mind. And why does this make it, so why is this form, the standard form, so much easier to graph, right? So what we said was the easiest way to sketch a graph of a quadratic is to put it into standard form. Hey, Emily, that doesn't sound very easy because I have to complete the square. That's hard. The reason, okay, the standard form, the reason we want the quadratic in standard form is because it makes it really easy to find what's called the vertex of the quadratic. Okay? Is because, well, let's see here. It is the easiest way to find the vertex of a quadratic. Okay. So what does that mean? Well, it means that we have something like this. So an x squared, remember, we talked about those core functions that we need to know kind of the general shape of. So x squared is something like this. If the coefficient is positive, right, it could also be facing down. I'm kind of like that down. I'll draw it instead, that's better. So here, actually, maybe I'll do it kind of, so here, this is some sort of quadratic, okay? And down here, that's the vertex, right? So the kind of the cusp of this parabola, this is the vertex, okay? Notice that if it's pointing up, right, then this little vertex here is the minimum of the function, right? Which might be useful, and I'll show you when it's useful, right? So here, if the parabola is pointing up, okay, how do we know if it's pointing up? Well, we can look at our original, so the general form, right, or the standard form. Either way, there's an A here and an A here. This A is the same, okay? So here, the A's are the same, okay? So what happens, right, is you have this A and it reappears here. So this A tells us if it's pointing up, right? If A is positive, then it's pointing up, and if A is negative, then it's pointing down. Okay, so we can learn a lot from just looking at the function. So if the parabola is pointing up, A is greater than 0, right? So A is positive. Okay. Which means, okay, so if it's pointing up, right, then the vertex must be the minimum. So if the parabola is pointing up, A is greater than 0, and the vertex is the minimum. Okay. What about if we have something like this? Okay. That's a quadratic, right? It's some sort of parabola. And here, right, we know that this is the vertex again. But now it's pointing down, so A must be negative. And now it looks like the vertex is at the top of the mountain, right? So it's at the maximum. Whereas if A is less than 0, right, the vertex is the maximum. That's going to be really, really useful, right? To be able to find either the minimum or the maximum, it depends on which way it's pointing, right? But to be able to find the vertex is really, really useful. Okay. So from standard form, so if a quadratic is in standard form, the vertex is at HK. Hey, f of x is a times x minus h squared plus k. Okay. Notice that this here is a negative, right? So it's negative 8 or minus h. So if you have x plus 2 in here, then h must be negative 2, right? So that's the only kind of tricky part, right? And then k behaves the same way that you think it does. Okay. Notice if f of x is 3 times x plus 4 squared, oops, minus 3. Oh, maybe I should use a different number than I already used. It's hard to think of numbers. Minus 9, let's say. Okay. We know a lot about this function already, right? What are some things we talked about? Well, a here is positive, right? Okay, so if it's positive, it's pointing up, which means my vertex must be a minimum value, right? And I also know what the vertex is. The vertex here, h, has to be negative 4, and k must be negative 9, right? Plus k, but it's minus 9, so must be negative 9. So here, oh, I'll keep the same color. Since a is 3, which is greater than 0, the parabola is pointing up. Oops. Parabola. The parabola is pointing up. So the vertex is minimum, right? Just imagine, okay, if I'm pointing up, then the bottom must be a minimum. Is a minimum. And h is negative 4, right? Just kind of make note of that negative. Oops. And k must be negative 9. So the vertex is at hk, which is negative 4, negative 9. Okay. Just from this, right, just from knowing where the vertex is and which way it's pointing, I can know a lot about this function, right? And so what I can do is I can just do a little sketch here. Okay, negative 4, so x is negative 4, so I'm over here somewhere, and then negative 9 is down here. Let's see, somewhere down here. Remember, I'm just doing a quick sketch, just gathering information about this thing, right? And so here, it's pointing up, so this is my minimum. So from here, right, I've got something that might look like this. This is a possible sketch. Okay. Just from knowing where the vertex is and which way it's pointing. Okay. Notice that just from the sketch, and I'll extend these axes so it's a little bit cleaner. xy. Okay. Notice that it looks like, well, I'll definitely have a y-intercept, right? I'm crossing the y-axis at some point. I will also have two x-intercepts, right? We've already talked about the roots of quadratics, where you have with Shaun. So the roots of a quadratic, right, are the solutions where y is equal to 0, right? So here on the x-axis, y is equal to 0, and on the y-axis, x is equal to 0. So here on the x-axis, y is equal to 0, and on the y-axis, x is equal to 0. That's going to be really useful for finding the x and the y-intercepts, right, which are an additional tool that we use to graph these functions. So, we see that there should be x and y-intercepts, which we can solve for. Which we can solve for and you can use either the general form or the standard form using either f of x equals ax squared plus bx plus c, or f of x equals a times x minus h squared plus k. Okay. Notice that, okay, so the x-intercepts happen when y equals 0, right? So if you just kind of remember if you sketch out your graph here, your x-axis, then convince yourself, okay, that's when y is 0, right? So you don't need to remember, or you don't need to memorize how to find the x-intercepts and the y-intercepts. You can kind of get there on your own and say, well, at these points, right, the x-intercepts, which are the roots of this quadratic, which sometimes we call it the zeros, the roots, the solutions, kind of depends. I know that's hard in the beginning to keep track of all these words that mean the same thing, but all we're talking about is the x-intercepts. And so the x-intercepts are when y equals 0. The y-intercept is when x is equal to 0. So typically the x-intercept is quite easy to find. Did I say y-intercept or x-intercept? The y-intercept is the one that's easier to find. The x-intercept, because there are two of them, right, it can be a little bit trickier. So from here, okay, what do I want to say here? The x-intercepts happen when y is 0, right? So remember, y is used interchangeably with f of x. So here we have f of x, which is really y. Y equals ax squared plus bx plus c. Okay, so we're forcing this to be equal to 0. So we can find the x-intercepts from f of x equals ax squared plus bx plus c, right, using the quadratic formula, using x is negative b. You probably have the quadratic formula memorized right now, or by now. Negative b plus minus the square root of b squared minus 4ac over 2a. Okay. or f of x equals a times x minus h squared plus k by solving for x, by letting f of x equal to 0 and solving for x. Okay. So you would have numbers, so 0 equals 3 times x plus 4 squared minus 9. You can solve for x, right? Just as an example, right? So you have two different ways of finding the x-intercepts. Pick one and stick with it. You don't have to do both, obviously. They're gonna get you to the same answer, right? The y-intercepts happen when x is 0, right? So here, the y-intercept happens when x is 0. So all you have to do is you have to plug in x is 0 into either of these, either in the top one or the bottom one down here, and the result is the y-intercept. So the y-intercept, the y-intercept happens when x is equal to 0. So we can find the y-intercept. So we find the y-intercept by letting x equal 0 in either f of x equals ax squared plus bx plus c, or f of x equals a times x minus h squared plus k. That's a k. Okay. So you would just let x be 0 and then solve for f of x, which is your y, and that's your y-intercept. Okay. Let's make sure before I flip the page here, I kind of went off on my own little rant here. I'm covering all the material, but in my own way. Let's see here. What if, consider something like this. So if you had a graph that looks like this, so here's your vertex and it's pointing up, right? You're not expecting to find any x-intercepts, right? So there is a y-intercept, but no x-intercepts. Okay. It's important, right? Because what we can find, so we know from the vertex, right? If you're able to put things into standard form, you know what the vertex is. It's at HK. So you know where the vertex is. And from from the standard form, let's talk about the standard form, you know if it's pointing up or if it's pointing down, right? So if it's pointing up, if the vertex is here, let's say at 2, actually, let's call it 3, 2, because I drew it kind of weird. At 3, 2, okay, let's say that's your vertex. And if it's pointing up, you're not expecting to find any x-intercepts, right? So it's a good check-in point before you go ahead and try to solve for something. So now, if it was pointing down, right? Then, so if the vertex is at 3, 2, but if A is negative, then it's pointing down, right? All of a sudden you are expecting x-intercepts. So you can use the vertex and if it's facing up or down to tell you what to expect to find, right? Are you expecting to find x-intercepts? Are you expecting, you're always expecting to find a y-intercept because the domain is all the x values, right? the domain of any quadratic is the set of real numbers. Okay, so you'll always cross the y-axis eventually. Okay, but before I get too deep, how about we do an example? Let f of x be 3x squared plus 6x minus 4. Okay. A, put f of x into standard form. Find the vertex, so this is part B, find the vertex, the x and y-intercepts. Sketch the graph. Okay. So remember what we said here. Okay, to put something like this into standard form, we have to complete the square. And so what I'm going to do is I'm just going to steal it just as a quick reminder here, because it's been a while since we completed the square. Probably, hopefully, maybe. Not hopefully, actually, just probably. So we're going to complete the square. Notice that, whoops, whoopsie daisies. Copy. Okay, I'm going to bring it down here. All right. Notice that we need to have just x squared plus bx. In our case, we have some sort of ax squared. Already, I know this thing is pointing up, right? Just from looking at this, I know a is positive, so I know it's pointing upwards, right? So I already have some clue about what this thing looks like. So x squared plus bx. So what I have to do is I have to pull out this common factor from my x squared and my x. So a common factor of 3 has to get pulled out from my x squared and my x. Notice I don't care about the 4. What's going to happen is it's going to go on the outside, and I'm just going to focus my attention on the x squared and the x, because that's what I need. I need it in the form of x squared plus bx. So here, what we need, we need to extract a common factor of a to write actually not to write. I'll just do colon and then I'll just do it. So f of x equals 3x squared plus 6x minus 4. Okay, so what I'm going to do here is I'm going to say, well, I'm going to pull out a 3 times x squared plus 2x minus 4. Just do a check-in point here. Notice that the negative 4 kind of stays on the outside. So here I need to focus, because this is the form that I need to complete the square. So notice that if I expand this in, 3x squared plus 3 times 2x, that's 6x, and then minus 4, I haven't changed this thing at all. So that's what you need to make sure of. Because this is the form needed to complete the square. Okay. Because, right, to make x squared plus bx, in this case we have x squared plus 2x, so b is equal to 2 in this case, a perfect square, you add b over 2 squared, which is weird, right? But you have your b from here, so b over 2 in our case is 2 over 2 squared. 1 squared is just 1, so we're not doing anything crazy here. Sometimes it can look a little bit weird, but for this kind of starting problem, it's not going to be that weird. So what we have to do is, okay, if I'm adding, so I have this part, right? X squared plus bx. And then what I'm doing is I'm adding b over 2 squared. If I'm adding it, I also have to subtract it, right? I can only add 0. So here's what that's going to look like. So we have to have 3 times x squared plus 2x plus 2 over 2 squared minus 2 over 2 squared. Okay. Add 0. Because I'm adding 2 over 2 squared, but then I'm also subtracting 2 over 2 squared, right? And this is what we call completing the square. Add 0. Yep. And then remember, on the outside of these brackets, we have minus 4. Okay. So here, I'll make a note that this b is equal to 2. So this is going to be b over 2 squared, which is 2 over 2 squared. Okay. So what happens is we regroup again. Okay, so now completing the square says that if I have something like x squared plus bx plus b over 2 squared, I can rewrite it as x plus b over 2 squared. Okay, that's kind of weird, but it's a perfect square. So that's what completing the square means. And so now I'm going to regroup this because this right here is a perfect square. Oopsie daisies. Perfect square. Okay. Noticing that this 3 is multiplying this 2 over 2, right? So it's still inside the brackets, so you don't want to forget about that. But what we're going to do is we're going to rewrite this as a perfect square, and then we're going to expand this 3 in to slowly get it into the standard form. So what we have is we have 3 times, and then our perfect square, which is going to be x, and I'm going to refer to this here, right? X plus b over 2, so b is 2 in this case, 2 over 2 squared. I'm showing that I have 2 over 2, so I'm not simplifying it to 1 because I don't want it to disappear for you guys when you're looking back at these notes. But obviously, if you're working through it on your own, then you can. So x plus 2 over 2 squared, okay, and I'll put a bracket around 3, minus, and then I have 2 over 2 squared, and bracket minus 4. Okay, so this here is your perfect square. Right. So this lump became this perfect square. Okay. So we're really close to being in standard form now. So what we have is we have 3 times, you know what? I'm going to simplify this 2 over 2 to be 1 now because we're kind of ready for it. X plus 1 squared minus 1 squared minus 4. 1 squared is just 1, right? But in order to bust out these square brackets, what I have is I have 3 times x plus 1 squared minus 3 times 1, and then minus 4. puts me at 3 times x plus 1 squared minus 3 minus 4 minus 7. And I wish I had, you know what? Just to keep it on the same page here, I'm gonna just bump things up by 1. Okay, how about there? By 1 line. Otherwise, I'm dealing with a page break here. Nice. So this now, this is in standard form. Woohoo! Right? A times x minus h squared plus k, right? So here, what we need to be careful with is that h is -1 and k is -7. And I'll scoot this over in standard form. So the vertex, hey, why did I write it on a slant like that? I'm not gonna do that. This is in standard form. Oops. With the vertex equal to hk, which in this case is going to be -1, -7. Okay. Just looking here. We already decided that this thing is pointing up, right? And so since A is positive, right? So since it's positive, it's pointing up. And you know h is -1 and k is -7, so you know where the vertex is. Okay. Since a is 3, which is greater than 0, this parabola is facing up. So we have something like this. -1, -7. Oh, whoops. Maybe I should draw it like kind of weird this time. So -1, -7, let's put it down here. Something like this, right? So here's the vertex. Vertex is at -1, -7. Okay. But knowing that it's pointing up, right? Then I suspect I have something that looks like this, right? So we expect to find x-intercepts for this one. So we expect to find x-intercepts. Okay. So let's see here. Kind of got ahead of myself here. So put f of x into standard form, which we did, and then we jumped at the chance to find the vertex. And so now I'm going to look for the x and y intercepts, and then using those, I'm going to be able to sketch the graph more properly, right? But I know it's going to have this general look, right? We just need to figure out what these values are. So the x-intercept, the x-intercepts are where y is 0. Okay. So we have 2 ways of finding these. We have 2 ways to find the x-intercepts. Use whichever method you prefer. Use whichever method you prefer. Oh, what happened there? I don't know what happened there. Option 1. From f of x equals, let's say, what is it? 3x squared plus 6x minus 4. Use x equals negative b plus minus the square root of b squared minus 4ac. 2a. Right here, a, b, c. A is 3, b is 6, and c is negative 4. Oops, that should be a negative 4. Yeah. So we can solve the roots here. So negative 6 plus minus the square root of 6 squared minus 4 times 3 times negative 4 and over 2 times 3. I get negative 6 plus minus, and so 6 squared minus 4 times 3 times negative 4. Puts me at 84. So the square root of 84 over 6. And I'll do the square root of 84. I get 2 root 21. So on my kind of fun calculator here, it just gives me the exact answer. That's not always the case. It depends on your calculator, right? And so it just depends on the calculator that you have. It might give you a decimal approximation, which should be 9.165, blah, 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 blah. But just remember that that's a decimal approximation, right? And so you could pull out some common factors here. It looks like we can pull out a multiple of 4. Square root of 4 is 2. But let's see what happens if I put it into Desmos, the Desmos calculator. So there's Desmos for graphing and there's a Desmos calculator. Both are available for free. And so here's the Desmos calculator. And I'm just hoping my Zoom doesn't clunk out because it did do that before. All right, so I have 6 squared minus, and in brackets, I have 4 times 3 times negative 4, I think it was, 84. Okay, so far so good. Now I want to take the square root, oops. Backtrack that. Okay, the square root of that answer. I always like to use a square, the answer button if I can, which is here. I don't have a pointer, so it's right next to the plus sign, the ANS button, puts in the previous answer. So it looks like it doesn't give me the exact answer, it just gives me the approximate answer. Okay, that's all right. No big deal. But I'm going to use the exact answer. Negative 6 plus minus 2 root 21 divided by 6. Okay. Either way, you'll use decimal approximations likely for graphing, right? Because it's hard to know where 2 root 21 is, right? Really hard, actually. So I would probably just, if you don't have the exact answer, that's okay. Sometimes I think Shaun might ask for the exact answer, so just know that that's what this is. But here, what we're solving for, right, is when this thing, this f of x equals 0, and so x equals, and we get 2 answers, x equals negative 6, okay, here we go, negative 6 plus 2 root 21, Oh no. Whenever my phone goes off. Okay. I lose you guys for some reason. There we go. Oh, I think we're okay. Yeah. So we have -6 plus 2 root 21 over 6 and -6 minus 2 root 21 over 6. So -6 plus, and then I'll put in brackets, oh I have plus plus, 2 times the root of 21 divided by 6. So I have x is roughly equal to 0.5275, 252317. I guess I can go there. 52752 52317, and I need more room. And if I do the same thing, so -6 minus 2 times the square root of 21 end bracket divided by 6, then I get roughly -2.527525232, but I ran out of space. So that means that we have x-intercepts. Remember, these are the x values when y is 0. So the x-intercepts are at, and I'm going to list them from left to right so I don't forget about any when I'm graphing them. Right, so I'm going to do this one first. -2.5270 and 0.52750. And I guess I should put another 5 there. Same number of decimal places for both. Okay. Notice that they're the same, 0.5275. But it's hard to find that relationship. You need to calculate it. Okay? So that's your first option. Okay. If you prefer to use the quadratic formula, that's great. That's fine. Just know that what you're doing is finding the x-intercepts. Option two is from the standard form, from f of x equals 3 times x plus 1 squared minus 7. 3 times x plus 1 squared minus 7. And I don't know if I had a space. Okay. Let f of x equal 0 and solve for x. So we have, and I'll start properly, f of x equals 3 times x plus 1 squared minus 7. So 0 is 3 times x minus 1 squared minus 7. Notice that the only variable here is x, right? So I'm able to rearrange things if I just be patient, right? I have to add 7 to both sides, divide both sides by 3, square root that. Square rooting gives me the positive and the negative, so that's how I'm able to get those two values. That's always going to be the case here. If there is one x-intercept, there will be two. It's possible, like we saw, right, that we have no x-intercepts. Right? We're above the x-axis, we're pointing up, there's no way we're crossing the x-axis. Same thing if we have a negative vertex and we're pointing down, there wouldn't be any x-intercepts, right? So there are scenarios where there are no x-intercepts, right? In this case, we know that there are. So we get 7 is 3 times x minus 1 squared. 7 divided by 3 is x minus 1 squared. So the plus minus square root of 7 over 3 is x minus 1. So then we get plus 1, which I'm actually going to put out front here just to make it look a little bit nicer. So then I have the plus minus root of 7 over 3. I'll do it here. But then when I rewrite it, I'm going to have x is 1 plus minus 7 over root 3. Okay. You already put in a ton of work to find the standard form. I think it's easier to use option 2 to find your x-intercepts, but I'll leave it up to you to figure out which one you prefer, right? Because here, now we can find the x-intercepts. So x is roughly 1 minus the square root of 7 over 3, which is, why is it negative? Oh, plus 1. Why isn't it working? 7 over 3. Okay. The root of 7 over 3 plus 1. Okay. I must have just hit something wrong. But let me try. 1 plus the root of 7 over 3. 1 minus the root of 7 over 3. Careful, Emily. Careful. Why did I switcheroo this? I shouldn't have. I got greedy. If we were only adding, it would work. But because I'm adding and subtracting here, the positive and the negative, negative 4 plus 1 is not the same as 1 minus 4. So obviously, when you put it that way, right? So you can't switcheroo these. That's fine. I'm getting, so if I do root 7 over 3, oops, plus 1, I get roughly 2.5275. And if I do negative root 7 over 3, right, the negative's on the outside, plus 1, then I get hey, what's going on here? Why is it negative? Okay. What did I do wrong? Sorry, say that again, David.
I'm confused.
You and me both.
Why wouldn't you be, at least for the plus minus root 7 over 3, why wouldn't you be able to just have the 1 on either side?
I know, well, mostly because it's not working. So I convinced myself that it's because I'm doing 1 minus root 7 over 3. There's only one way to get to the bottom of this and see which one I messed up on, and that's using Desmos. So what I'm gonna do, Desmos will tell me what's going on, the graphing one. So what I'm gonna do is I'm gonna graph these. First, 3x squared plus 6x minus 4. Hey, 3 squared. 3x squared. Not to the power of x squared. There. So now my vertex is what I found. Okay, so my first x-intercepts were correct. Now let me just graph 3 times x plus 1 squared minus 7. They're overlapping, which is a good thing, right? The red function is the original function, and then I put it into standard form. Hopefully I haven't changed anything. So if you're working through these problems, you can graph them just to make sure that you have the same function still, but then also kind of cheater way, it'll highlight where all the x and y intercepts are in the vertex. Okay, so I'm obviously messing something up in the second one because it looks like what we found up here is correct, right? Negative 2.5 and 0.5275. Okay, so what happened here? I feel like x plus 1, okay. Added 7 to both sides, divide by 3. I'm just so confused because it's not hard. Plus minus 7 over 3, plus 1. Da-na-na-na-na-na-na. What happened? I went from plus 1 to minus 1. Plus 1, plus 1, plus 1, plus 1, minus 1, minus 1. Okay, that's what happened. Flew too close to the sun here. Okay, so now when I do the root of 7 over 3 minus 1 does put me at the right intercept. So 0.527, blah, 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 and negative root 7 over 3 minus 1, negative 2.527. Okay. These are the same x-intercepts that I found earlier. So that was my big mistake, my critical mistake. I copied it out correctly, so I don't know how it happens. Good. So just, you should be using Desmos to check your work, right? Check yourself just like I did when things are kind of not working out. And you just want to make sure that the x-intercepts you found are the right ones, right? And so it looks like they are. And so the y-intercept moving on to the y-intercept is where x is equal to 0. So in either function, oops, missing an I there. In either function, let x equal 0 and solve for y. So f of x is, let's do 3 times x plus 1 squared minus 7. So f of 0 then is 3 times 0 plus 1 squared, squared minus 7. 0 plus 1 is 1, 1 squared is 1, times 3 is 3, 3 minus 7, here we go. 3 times 1 squared minus 7 is 3 times 1 minus 7, which is 3 minus 7, negative 4. So then our y-intercept is at 0, negative 4. Right? And you would find the same thing using the other equation, right? So using this one here. But what I like to do is once I have it in standard form, I just like to use the standard form. I worked hard to find that standard form, but if you want to check yourself, then you can do them side by side until you've picked a favorite. So now, right, if we write the x-intercepts out, x-intercepts are at negative 2.5270 and 0.5270. So now to sketch this graph, we can just plot these points. To sketch the graph, plot these points. And maybe, you know what, I'll use a little grid here, why not? Sticky's grid, because I've got some space here. All right, I'm gonna put my y-axis over a little bit. And hopefully I made, because I need my vertex, remember, is a -1, -7. So if I let this be -1, -1, 2, 3, 4, 5, 6, 7, looks like I have enough room. So that's good. So the vertex, actually let's label some of these just so we have an idea of the scale. Hey, 1, -1, come on. 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Good. I guess. All right. So the vertex is here at -1, -7. Vertex is at -1, -7. Oops. I always do that little twiddle in front of 7 instead of just a negative. So that's the vertex. And then most recently, I found the y-intercept is at 0, -4. So 0, -4, the y-intercept is at 0, -4. Okay, so I know I'm going to cross the y-axis here at 0, -4. I also found roughly the x-intercepts, right, because these are approximations, at -2.50 and 0.50, right? I don't have a great scale, so -2.5, -2, -3, -1, 2, -2.50. So the x-intercept are at -2.50. Let's call it -2.527. Now let's leave it. And positive 0.50, roughly. Okay. So now I have all the components that I need to be able to sketch this, right? It's going to be quite a closed parabola here. But what I'm going to do is I'm going to try to, whoops, it's hard. Probably easier to start at the vertex and run through. Okay, this is the hardest one. Not very beautiful, but it works. Finally, the last thing that we need from this thing is the domain. The domain for any of these quadratics is going to be the set of real numbers. So x is in the set of real numbers or from -infinity to infinity, whichever you prefer, right? Interval notation or kind of set notation. The range, in this case, right, the range is the y values. So it starts at -7, it includes -7, and then it goes up to positive infinity. So the range includes -7 and goes to infinity. There, I'm all out of time, but there are your quadratic equations. Any questions?
Not so much a question, but an observation, since I was doing the assignment in question and following along with this. Yeah, you really gotta watch out for your signs.
I know, they're such little buggers, right? And you saw it, I get tripped up all the time, but just if you graph them in Desmos, then at least you have kind of a roadmap.
Mhm.
You kind of know where you're going. So
Okay.
I would say use that.
All right. I shall see you Friday then. And
Sounds
yeah.
good. All right. See you guys on Friday.